Give this one a shot. Thumbs up when you have a guess. Have a conversation. Tell them why you think so.
What's your video?
Gravity is down. The force of air resistance the entire time is pushing it down to go. The force of air resistance is decreasing. Yeah, is decreasing as it's slowing down. As the ball is going up, it's slowing down. So the air resistance is decreasing. There's less friction.
Decreasing.
So yeah, so because the air resistance is decreasing,
There's no resistance.
yeah. You understand what
So decreases.
and just to cover
That decreases in that lower.
Correct answer is? Correct answer is E. Good job. The force of gravity is always acting down. Air resistance, as it goes up, is also acting down. And it's dependent on speed. So the slower it goes, the less air resistance is acting on it. Good with that? Okay. Same scenario. This is for the up and the down. The whole, for the magnitude of acceleration for the whole process, up and down. Right after it's thrown and right before you catch it. Thumbs up when you have a guess. Question. Nope. Right before it's caught. Right after it's thrown. Have a conversation.
It depends.
Acceleration in the same direction.
We should really watch that lecture.
Originally, you have gravity plus then you have just gravity, and you have gravity minus surface.
It's going up. It's going down.
I don't know what the summer show is.
What you can't teach people.
I smile when I'm telling the truth. I do not know what the country is.
What do you say? Correct answer is C. Okay, as it goes up, air resistance and gravity are both acting down, so you have a net force that's greater, but air resistance decreases. Initially, you've got gravity and air resistance. As you go up, it slows down. Gravity is still a thing. Air resistance is decreasing. At this highest point, there is no air resistance because it stops. You still have gravity. So this is like 9.8 at the highest point. Okay. As it goes back down, gravity is still a thing, but air resistance is now kicking in, going the opposite way. Okay. So this is going to be less than 9.8 over here. It's going to be greater than 9.8 here. So it's a decrease the entire time. Good. Okay. Last question in this cycle. Oh, just kidding. Nope. Second to last question. Wait for it. Wait for it. Thumbs up when you have an answer. Have a conversation.
Also, it's
That sounds right. But I think it's. Wait, I think it's either B or it might be this. And just say. Yeah.
Going up, no matter what.
But its initial velocity is
No matter what.
I think it makes up Susical.
Why do you think it's its initial velocity is faster?
She said that when we were thinking about your
The slower it's going, the less air resistance. So I think it's
No. You don't need more guys.
Yeah, I'm sure that's right, but my feeling is
I think we would actually be more pros than
on the way up, there's always a height that is going towards a stop quicker. And on the way down, you see, that's the perfect way to and for it to be the same or
Time to get to the end a little bit.
okay, I guess fair enough. If we are accounting for it just in gravity, then yes, it would depend. So depending on this acceleration of the connection, I work
Actually, for example, don't throw it.
Wait, that would still the same.
All right. Do you have any conclusions? This is a good question. Like this is a challenging question. What do we say? Correct answer is B. Here's my argument. So going from the bottom to the top, this has a certain initial velocity, and its final velocity is equal to 0. And it covers a certain distance, x, y, whatever. Okay. Coming down, its initial velocity is 0. Its final velocity is something. Faster, slower, or the same as what it was thrown at, do you think? Slower. You okay with that? It's covering the same distance. They have, this side has a smaller change in velocity than this side. Therefore, from here to here, and we know also it has this side has a greater acceleration going up than going down, right? Because it was decreasing the whole time. So it's going to take more time to do this route and less time to do this. Okay with that? All right. Last question on this series. Probably should have asked this one prior to that last one, but thumbs up when you have a guess. Have a conversation.
I was thinking for a second, and I realized. I'm not the no, it's gonna have to get.
Yeah, really.
So it's a
For 50 years.
alpha.
So,
Has that ever played chess? He's really good at checkers.
VI.
It's basically
That is true. I don't think he cares enough to play 3D chess.
Correct answer is? Correct answer is A. Okay. The force of air resistance is greatest from here to here, where it's the fastest. You okay with that? Okay. All right. Let's,
What do you think are the odds that, like, on an AP test we get a question like that where it asks us like position as a function? Like,
pretty low.
pretty
Pretty low. Okay, so the chances of getting an air resistance question for a free response, I'd say is about 25% chance. Just on a normal year. So you'll see it somewhere, either in multiple choice or free response. They do a really good job of hitting all the topics. James.
When we get an air resistance question, will they just like simply just tell us like, will they just like not tell us to ignore air resistance, or will they tell us to like?
No, they'll say it has some resistive force, function negative BV, or it has air resistance, or experiences drag, or I mean, this could be in, like I've seen them like in water. You have like some kind of drag force in water or air, something. I mean, it's pretty explicit. Like they won't be able. They're not trying to sneak that under the rug. Like, it's like this is the question. And
you said there's a 20% chance of there being one. Is that like 20% that a given problem is air resistance, or 20% that
no,
all of the problems include one air resistance problem?
of all the free response problems, one of those is air resistance. So
Is that empirical? Did you count?
No, that's why I said about.
Okay.
But
what are the odds that there's one on our test on Tuesday?
20% chance.
So 20% chance that one shows up, or like 20% mean?
I just asked that.
It-
I feel like 20% meaning that there is like one of the problems will have air resistance.
20% chance one of the problems will be air resistance.
What are the odds that they all have air resistance?
Very small.
That would be.
I think we're also forgetting 25 over 20, so.
All right, here we go. Relative motion. Okay, this looks complicated. Hopefully I can break this down so it's not so like crazy. But this is like flying a plane on a windy day, swimming in a river with a current. These type of questions. Okay. This is like hardcore. Rarely do you have. I actually have never seen a hardcore math problem where it's like two-dimensional. This is more math class type stuff. You could take this to math, but the idea is the same. So these are all vectors. Probably should have put a notation here. That just means it's a vector. So direction matters. So this is the subscripts tell. This would be the velocity of the object relative to the Earth. This would be if you're swimming in a river, how fast let's say you're watching your friend's watching you swim in a river. This is how fast your friend sees you swimming relative to where they're standing on the bank. Okay. This is the velocity of the object relative to the medium. So this would be how fast you're swimming. If you were swimming in a pool, you're not changing anything. If you're swimming in the river or swimming in the pool, you're just swimming. It's how fast you're going relative to the medium. Okay. And the velocity of the medium relative to the Earth, this is how fast the the river is flowing relative to your friend standing on the bank. Okay, so the way I remember this, I don't have this memorized. I actually recreate this. So usually what we want to know is how fast does our friends see us. That's like the objective. And so to achieve that, it's kind of like doing fraction math. You have object relative to the medium, and then medium relative to Earth. You don't actually do this mathematically. This is just how I remember this. That cancels, and you're left with object relative to the Earth. That's how I remember that and reconstruct that equation. Okay. Now, it's a vector, meaning that we can break these vectors up into x components, and this relationship is true. And we can break this up into y components, and that relationship is also true. Good with that? Bunch of motors on the middle table there. You may. Okay. So, okay, for the sake of time, let's see, what are you doing? You're swimming. So 3 meters a second. You're you're able to swim at 4 meters a second. So resultant relative velocity is head to tail, 5 meters a second. You all right with that? Okay. Doing this is an overkill for this problem, because you just get, if you're looking at x direction, this is, you're not swimming in the x direction. It's just in the y. So this is 0. Your river was 3. So your x component was 3. And in the y direction, you're swimming at 4 meters a second. The river is going 0. So your y component is 4. And then you have to find the resultant of 3 and 4, and that's 5. Okay. That's not worth it. Okay. That's math class. We don't need to do that. Yeah, you can also do this with acceleration. Okay, it's the same relationship. Usually this is like one-dimensional stuff. Here's where you'll see it on physics. Have a conversation. Think conceptually. Let me just throw that out there. Okay, when I'm saying hit the ground, this ground of the elevator. Okay, have you guys ever done something illegal by like holding something in a drop zone, a Tower of Terror, where they do the ride and they drop you? You hold something and it floats. No.
We don't have we're not supposed to do that, Mr. Smiley. That's against the rules.
You're right.
We're also not supposed to tie it.
It's gonna float. Okay? The relative acceleration would be 0 because you are experiencing acceleration and the object is experiencing acceleration. So the object acceleration of the object relative to the medium would be the elevator. This would you are that's what we're looking for. No, this object relative, so this would be 9.8 meters per second squared downward. Okay, the object, yeah. This would be the acceleration of the medium relative to the Earth. The elevator itself is moving at 9.8 meters per second squared downward, and so the acceleration of the object relative to the medium would end up being 0. Because both are accelerating. Does that make sense? Okay, so, oh, look at me. Yeah, okay, so it would never hit the ground while it's falling. Just float there. So that's 0.
And then you hit the ground and you immediately get crushed.
Yeah, well, hopefully not, but all right, so we're moving downward. We're accelerating downward at a rate. We're speeding up, moving downward 2 meters per second squared. Have a conversation.
That's right. Because it's just a lot.
Okay. Wait,
Okay, correct answer is C. Okay, here's the math, and I'll do a concept. Okay, the acceleration of the object relative to the Earth, negative 9.8. The acceleration of the medium relative to Earth, that is negative 2. So the acceleration of the object relative to the medium would be a negative 7.8. Okay. Conceptually, here's how I do it. If I drop the rock, would it take longer or shorter amount of time to hit the ground, to hit the floor of the elevator? Take longer. The floor is accelerating away from me. Okay, so that's going to act like it's a smaller acceleration. Good with that? Is everybody okay with E? Okay, you have a positive 3 now because you're slowing down while moving downward. That rock will hit the ground sooner. It's just slowing down. Okay? All right. So, needed to build that foundation to have this conversation, which we'll see if we get through. So the conservation of momentum can be applied for any inertial frame of reference. This is kind of getting at what you're doing with the gravity lab when you're changing the frame of reference. Okay. So an inertial frame of reference is one that is not experiencing acceleration. So you can be at rest, you can be moving, like it's okay, moving at a constant velocity. Anywhere where inertia is doing what it wants to do, that's an inertial frame of reference. Okay. Yeah, forget that. Okay. So, this is a lame video. Refer back to your experience with the gravity lab where you were doing the not following the center of mass and then following the center of mass. Okay, that's what that video is trying to show. Poorly it shows. All right, so we're starting with this scenario. Nothing's weird. Okay, everything works the way we expect it to work. How'd you set this up? So everybody goes B. Goes that. Okay. So now, thumbs up when you have a guess. Have a conversation. Correct answer is There we go with A. Okay. Relative. Okay. Think of it this way. You're sitting in a car driving, and the passenger, relative to you, how much momentum does that person have? None. Relative to you. Now, you could be driving at 60 miles an hour, and someone outside the car from a different inertial reference point sees you both having momentum, but you see your passenger having no momentum because they're sitting at rest relative to you. You okay with that? Okay. So that's what this is getting at. Next question. Tell your neighbor.
Yeah.
Okay, yeah, it's because I was thinking if it's gonna be one positive, because it's going in the other direction. Yeah.
Correct answer is? Correct answer is C. Good? All right. You're moving the frame of reference going this way. You ended up throwing it that way. It's going to go faster because you're going away from it. Okay. You're welcome. Thumbs up when you have a guess. Correct answer is? Have a conversation.
So then
And then
I'll let you know
from the perspective of this bird,
is 5 years. So the rest is 100, then the part is going to be 95. And then next momentum is going to be 1/3.
Correct answer is? So everybody go with C. All right. Like that. That's what this is building us up to. Okay. What we want is we want all the velocities to be from the same perspective, same frame of reference. This is from the frame of reference of the moving car at 2 meters a second. This also is from the perspective of the frame of reference. You good with that? Okay. Let me, okay. With this, object relative to medium plus velocity of object, no, medium relative to Earth. So I am looking for that. We said that this was 20, and this is positive 2. Does that make sense where we're going there? Okay. Now, all right, where are we going here? Okay, so I guess what I'm trying to get at here is their velocities are going to be different. Okay. Are they contradictory? No. They just have different frames of reference. Are you going to have different momentums? Yes. That's what you found in the chart. Okay. Was the change in momentums different? No, the change in momentum was consistent. But the actual values, those dependent on velocity, that's a relative measurement. Okay. So this only works when you have the same frame of references. So here's what's wacky. Throwing at 20 meters a second relative to you, but their speed is relative to the Earth. So how fast are you going moving relative to the Earth after it's been thrown? So let's see what my next slide is. So think about how you would do this. I'm about to give you a whole lot of choices and it's going to look really overwhelming. So I need you to have something in your brain that you can discern, filter out what's good, what's bad. So I didn't change anything. I just gave you some choices. sake of time. So what we're arguing is this. Okay. So this is, I need the velocity of the object relative to Earth. That's what I'm looking for. Okay. I have the velocity of the object relative to the medium plus the velocity of the medium relative to Earth. Velocity of the object relative to the medium, this is the 20. Okay. And it's going in the negative direction. You okay with that? Plus, oh, wait a minute. Oh, yeah. Okay. This is my final velocity. Because this cart's going to be moving when you throw it, it's going to end up moving faster. It's not going to be going 2 meters a second. You okay with that? So correct answer is ooh. These are good choices. You are going to be going my brain says B, but I don't think that's. Yeah, that's right. B is right. B is right. Okay. Okay. Do you see why I had to do that? Because the velocity of the cart's going to be different when you throw it. So you can't just like take away from 2 meters a second. It's not going to be still, like it's still not going to be moving 2 meters a second. It's going to be moving something different. Okay. We'll pick this up tomorrow. I will assign something today.